In our last video, this problem created a problem. So in this video, we're going to resolve the problem. And the way we do that is by long division. I know you have all been waiting eagerly for this day. Polynomial long division, just like you did in Algebra 2. This is the only way we can find a slant asymptote. So, here we go. We're going to take the numerator divided by the denominator, just like a division problem normally is set up as. And now we have to figure out what to do. So, rather than trying to take this whole thing and figure out, how many times does this go into that, let me offer an alternative approach. Whatever goes here, I'm going to multiply by x cubed minus x plus 1. For example, just like if I were to take 18, whoa, that's not what I wanted to do. Okay, 18 divided by, 300 or 3,812. I would ask myself, how many times does 18 go into 3? 0. How many times does 18 go into 38? 2. And then we take 2 times this. Our goal is to keep eliminating numbers until we get over here where the decimal point is. And then we subtract, and we go on from there. We bring down the 2, the 1, the 2. Now we ask, how many times does 18 go into 212? Or, and so on. And then that number goes there, and we just continue onward. So, long division of polynomials is similar in a way. I'm going to multiply whatever this is by x cubed to make the 5x to the 4th go away. I just can't look at that color anymore. That's awful. Well, that was even better. Okay. We'll just leave that alone. Something here times x cubed has to give me 5x to the 4th. So I know it's a power of x. I know it's a power of x because x times x cubed is x to the 4th. But I also put a 5 there so that when I multiply, I get 5x to the 4th. Big minus. Okay? And now when I subtract, those will go away, eliminating that term. But I also have to multiply 5x by everything else. 5x times negative x is negative 5x squared. 5x times 1 is 5x. Big, gigantic minus sign to remind us what we're doing. 5x to the 4th minus 5x to the 4th is gone. Perfect. Negative 3x cubed minus nothing. There's no x cubed term here. That's all right. Negative 3x cubed minus nothing is negative 3x cubed. X squared minus negative 5x squared. Yes, you need to be perfect with your signs here. One sign mistake is not good. 1x minus 5x. And 1 minus nothing. Okay. Good news, bad news. Bad news is we're using long division, which I agree is not fun. Good news is we don't have to go all the way. A slant asymptote is a line. Lines are written as y equals mx plus b. Here I have mx. Once I get the b, I'm done. I just got to figure out what the b is. something times x cubed has to be negative 3x cubed. So what times x cubed is negative 3x cubed? Negative 3. Big ginormous minus sign is going to cancel out those terms. Negative 3x cubed minus negative 3x cubed. Those go away. Everything else is remainder that I don't care about. I'm done. This is my slant asymptote. So for this problem here, slant asymptote is y equals 5x minus 3. That's as far as we have to go in our long division. Let's get this thing off the screen. When the degree of the numerator is greater than the degree of the denominator, slant asymptote is going to be the equation of a line y equals mx plus b. We get that equation by doing long division. Let's see what that looks like on a graph. So I'm going to graph this function. So we have 5x, whoops, let's start over. Parentheses for the numerator, 5x raised to the fourth minus 3x raised to the third plus x squared plus x plus 1. All that divided by x to the third minus x plus 1. If I graph that, I get this. I want to change the window. Let's make this 0 to, let's say, 50. So the function kind of comes down like this, really steep, and then it kind of goes up like that. Here's the slant asymptote, 5x minus 3. And it's a little hard to see. Let's see if I can make this a little nicer here. Let's try 30. Let's see what that does. A little bit. Let's zoom in on that a little more. If we zoom into this area here, here's the function, and then here comes the slant asymptote. And the area I zoomed in on there, there's a little bit of a gap. But if we go over a little more, let me just go back to a standard view here. If we go over a little more, here comes the, we see that they get closer and closer and closer and closer together. As x continues to grow, this line will, this function will approach this line, and we'll never get there. It is possible that this line could have crossed this function at one point, but in the long run, it will go back to just approaching it. So that is an example of what a slant asymptote looks like. Another example is probably necessary. Let's take a look at another one. We have x cubed minus 10x minus 75 all over x squared plus 2. The degree of the numerator is larger than the degree of the denominator. So, again, we need to long divide. And let's see what happens. I need something multiplied by x squared to give me x cubed. That something is going to be x. And now we multiply through x times x squared, x times 2. Big minus sign. X cubed minus x cubed, nothing. That's what we want. Negative 10x minus 2x. Negative 12x, and this drops down. Now look what happened. X squared goes in, oh, it can't. X squared cannot go into this anymore. This is bigger than that. So all the rest of this is remainder. All the rest of this is remainder. X squared can only go into x cubed, and it can only go into another x squared. Well, we don't have an x squared, so we're done. Slant asymptote is y equals x for this problem. Let's see if we can graph this one. We don't need that. Don't need any of that. Don't need that. X to the third minus 10x minus 75 all over x squared plus 2. We can eliminate this. We can eliminate that for the moment. Let's see what that graph looks like. We got this thing going on here. So let's actually let me zoom out a little bit. Notice we do not have a vertical asymptote because the denominator can never be equal to 0. So if I zoom in on this little, I'm going to zoom in on this little area down here. A little bit of a parabola vibe to it there. There is no vertical asymptote. Denominator is not 0. So let me go back to a standard view here. Function looks like this, and it's going to do that little wiggly thing and then come back up. If I graph y equals x, that should be our slant asymptote, and it appears that we have it. Here the function approaches it rather quickly. Here, as we go off in the distance, it's going to approach it from that way as well. So there is our slant asymptote. And let me just make this window, let's come down to negative 40 once. See if that's low enough. So it appears that our function kind of looks like this. And then our slant asymptote would look like this. So we have draw this. This is actually coming this way more. It's approaching. This is approaching that way. And our function sort of looks like this. Again, this will not cross. It will approach it really, really, really close. This will approach it really, really close this way. Here is our slanted asymptote that it approaches as x. As x gets larger and larger and larger this way, this function value gets closer and closer and closer to that dashed line. So that is how you find a slant asymptote. Use long division. Once you get to a point where you have mx plus b, or in this case we had mx plus 0, then you're done. You do not need to divide all the way through. Next video, I will have some more examples.